All right, friends, just getting started with our introduction to differential calculus. So there's integral calculus and differential calculus. The part we do first is differential calculus. Differentiate is comes from the word derivative, so that's kind of our big key word here in this section, this whole first part of calculus. And what is the derivative? So first of all, let's make sure we know what it is. It is the formula for finding the slope of a tangent line to a curve at a point. So let's make sure we're clear about what that is. So we have to differentiate between a secant line and a tangent line. So a tangent line is a line that just touches a curve at a single point, right? So we're trying to find the slope at exactly a specific point, which we'll talk about how to do that in a little bit. You already know how to find the secant line, so we just find two separate points and then compute the slope between those. So that's a secant line. That's very easy. I mean, you probably did that in high school or even maybe middle school. But it's not really finding us the slope at a point that we're really interested in. So part of our notation is that, remember, m, y equals mx plus b, m stands for slope. So when I put the subscript of SEC, that means I'm talking about the slope of the secant line right here. If I put a subscript of tan, I'm talking about the slope of the tangent line to a curve. So just you'll see that frequently, so that's what we're talking about. An example of this in real life is when we talk about velocity or speed. So we can talk about average velocity versus instantaneous velocity or speed. And so, for example, if we say, hey, I'm going to go on a road trip and we're going to go 300 miles and it took us 6 hours to get there, we can find the average speed over that entire trip. 300 miles divided by 6 hours is 50 miles an hour. That does not mean that you went exactly 50 miles an hour all along the trip. You probably went a little faster, you went a little slower, maybe you stopped to get lunch or something. And so the individual times, the speeds at your individual moments along your trip is constantly variable. But this is the average velocity. Versus if I said, hey, friends, what's the instantaneous velocity on your trip? You just simply look at your speedometer. Oh, right now I'm going 62, and I'm going to speed up to pass this guy. Now I'm going 73. So that's the difference between average and instantaneous. So we need both of them for lots of different work, but the derivative helps us find this instantaneous velocity or instantaneous slope at a certain point. Let's dig into this a little bit here. So what I've done here is I've made a, let me pull that out there, that's bleeding through there. Hang on one second. I've just sketched a line here. This is f of x or y, whichever you want to think of it, negative 2x plus y equals 1. And then I have a point here on this, 1, 3. And if I said, hey, friends, go ahead and what's the slope of this line? And you could find another point. For example, I marked this point right here. So we would look and say, well, this is 3, 7. And then I said, hey, what's the slope between those? Well, we would go y2 minus y1 over x2 minus x1. And I would get 4 over 2, which is 2. So that would be the slope of this straight line. Again, you have known how to do this. Notice that these 2 points are far apart from each other. I could pick another point on here, and we would be able to find the slope of a straight line. So what we're interested in now in calculus is this problem. So here we have the black line here is a y equals x squared plus 1. And so I want to know, hey, friends, what's the slope down here at 1, 2? What is the slope here? Well, in order to find that, we have to find 2 different points. So what I've done is I've chosen 3 different points, and I made them in different colors. So first I said, well, we want to know what the slope is here. Let's check this point here, 4, 17. And so then I'm using this as my y2, and this is my y1. Sorry, you're not in the frame there. And I did that computation here, and I made a little boo-boo there. So we found that this is a slope of 5. So from here to here is a slope of 5. But I think you would agree that that's probably not the slope here. This looks much less of a slope down here than that is if you think about it. Well, let's get a little closer. Let's improve it. Well, let's use the red point, 310. And notice that the slope has changed. You see that it's less now? Not much less, but a little bit less. And sure enough, we compute it again, and we get a slope of 4 less. Well, it's better, but it's not best. Let's try again. And I do a blue slope here. And so here's my first point, my second point, and now my slope is 2. This slope is closer to this secant line slope, but it's not quite there. So how are we going to resolve this? Well, we're going to do a little thinking, my friends, and here's what we're going to do. So we're going to pretend that we have some kind of a quantum ability to zoom in on the number line. And so we're going to zoom in on our curve. And I have a point x and f of x. That's just my point I'm talking about. I want to know what the slope is. But I'm going to find the point on the x-axis that's literally right next to this point. Now, I know mathematically you said, well, there is no point right next to, but we're going to pretend that just for argument's sake, that we can. We can zoom in on a quantum level, and I can find the next adjacent point. There's no way I can put a point in here. And so we're going to say that this distance from this point to this point is h, is what we're going to say. So this point is x, and this next point over is x, that point plus h. Then the y value, the f of x value, is not f of x evaluated at x, it's f of x plus h, because it's evaluated at x plus h. So now, do I actually have two different points? I do. And I can compute the slope just like we did before. So in general, I would have that y2, here's my y2, minus y1 over x2 minus x1. And I can simplify this bottom to just h. Now what we're going to do to make this work is I'm going to take the limit, and we're going to talk about limits a lot more in just a little bit, but this is just an introduction here to showing you why we're going to talk about limits. I'm trying to put it in context for you, why it's so important in calculus. Is we're going to talk about the limit of this h as it goes to 0, meaning it goes literally to the smallest possible value that can exist. Well, you know, as small as possible, getting as close to 0 as possible. But you know from our basic limit rules that I can't just substitute 0 in here because that would be undefined. So this is where all this limit stuff we're going to talk about in Chapter 2 comes into play, why we're going to do that. So let me just show you how it works. And again, we're going to do this in much more depth. I'm just trying to put this all in context for you. So let's say that I have my function here, the one we looked at, y equals 2x plus 1, and I wanted to look at what the slope is at 1, just like we did. Well, here's my first point, 1, 2. That's that first point we're looking at. Well, what's that next quantum point over, that next one? Well, it's 1 plus h, and 1 plus h squared plus 1. Notice I'm plugging in those values here into the formula. Well, I compute it, and I get this. Do a little FOIL method right here to compute the slope, and a little simplification, and I get down here, and then notice when I get here, all these h's cancel, and I'm left with 2 plus h, and the slope is 2. So again, my friends, I'm skipping through this. We are going to do this in very much detail in later videos, but I'm just trying to, again, put this in perspective for you. So that's the slope at 1. The derivative, like I said before, is the formula for finding the slope at any point. So in order to find that, I'm going to go back to my original function, and I'm just going to use my first point as any point. X comma, there's my x, there's my y. X comma, x squared plus 1. And then my second point, x plus h, that next point, x plus h squared. I recompute here, and then I get this, and we have to do some algebra here, and all sorts of things cancel out. I'm going to FOIL that there, distribute that negative sign, and then we're left with this. And notice, my friends, and I'm going to, again, we're going to talk about this a lot in greater detail. You're going to have a bunch of things cancel, and when you get done with that, you should have h's in all of your terms here. If you don't, you've made an algebraic mistake here. The h's will cancel, and you might be left with some h's, but then you evaluate. And so now this is the derivative, meaning that's the formula for finding the slope anywhere on that curve. If I want to know the slope at x equals 1, plug in 1, and the answer is 2, which we already computed. What if I want to change points and say, hey, what's the slope at 5? Well, 2 times 5 is 10. But that is the derivative for that specific curve. We come up with a new curve, we have to compute a new derivative. But that's the concept of derivative. I hope that puts this in a context for what we're going to be doing here. We're going to go into limits next and start digging into those, and then we're going to come back here and visit this again.